I wonder how these went for you. Let's go through them. First, we'll convert e to the n equals s, which is an exponential equation, into a logarithmic equation. So log, what's the base? Same as the base on the exponent, e. Remember, the log is always equal to the exponent, so we're going to write log equals n. And what are we taking the log of? What is the thing that you get when you do e to the n? It's s. And the way we would usually write this is ln of s equals n. Let's try 5x equals e to the y plus 2. Again, we're being asked to write this in terms of logarithms. The base on the log has to be the same as the base on the exponent. What is the exponent? Because that's what the log will be equal to. Well, the exponent is y plus 2. And then what is it that you get if you use y plus 2 as an exponent on e? We get 5x. And this would often be written ln of 5x. The parentheses are actually optional here. Equals y plus 2. When parentheses are not optional, so if you're taking the log of just a single term, like 5 times x, you don't need the parentheses. It's understood that you mean the log of 5x. Okay, converting in the other direction. Let's write ln of 7 equals x as an exponential equation. And you are welcome, as always, to write ln as log base e, if that helps you. And then what does that mean? It means e to the x will give you 7. Okay, last, what about ab equals ln of 2 minus x? As always, it's perfectly okay to rewrite the ln as log base e. And then what does that mean? It means, in terms of exponents, it means that if I take e and raise it to the power ab, what I will get is 2 minus x. Before we leave this build your understanding problem, I want to just go back to what I said a minute ago about the parentheses being optional on ln of 5x. And I want to compare that to ln of 2 minus x, where the parentheses are not optional. So what's going on here is that if you are just taking the log of a single term, it's understood that you mean take the log of that whole term. So do 5x and then take the log. Whereas if I were to write ln of 2 minus x, so that's two terms, right? 2 and x being subtracted from the 2. If I write it like that, what that is understood to mean is do the ln of 2 and then subtract x from the ln of 2. So that's different. It's not the same as do 2 minus x and then take the ln of that difference. Okay, so one term, you can skip the parentheses if you want to. More than one term, nope, you got to put them in. Okay, going on, let's do some evaluating of natural logs. We're going to do these first without a calculator, and then, now that we know how to use a calculator to evaluate logs, we'll use a calculator to check our answers. Now, to evaluate a log without using a calculator, one method, and the one I like, is to give that log a name, and I like to call it A for answer. So I'm saying, okay, ln of 1, whatever that is, I'm going to call it A. Why would I do that? Well, this means that, yeah, and let me go ahead and rewrite it with the E in case that helps you. What that means is that if I take E and raise it to the A power, I will get 1. Now, if I raise, there's only one power I can raise e to get 1. What's that power that always gives you a 1? Yeah, it's a 0. So this tells us that a equals 0. And again, that's because e to the 0 power would be 1. And then what was a? Well, a was just my name for ln of 1. So ln of 1 is 0. And if you ask your calculator for ln of 1, it should give you 0. Let's try ln of e. In other words, log base e of e. And I'm going to, again, give that the name a for answer. And again, introducing that label equals a gives us a chance to rewrite this as an exponential equation. So let's see, this would say e to the a equals e. Now, when I just write e, there's an invisible 1 exponent that's always there. You can always stick a 1 exponent on a number, and that doesn't change what it is. So I can see, since the exponents have to match, I can see that a must be 1. And again, that's because e is the same thing as e to the first power. And again, what's a? Well, a was just my name for the natural log of e. So we see that the natural log of e is 1. And if you do that on a calculator, it will also give you a 1. Let's try ln of e squared. I'm going to call that a for answer, which allows me to change this into exponential form. So log base e of e squared equals a is saying that e to the a power equals e squared. In other words, a must be 2, because the exponents have to match in order for the expressions to be equal. And then what's that telling me? Well, a was just my name for the ln of e squared, and we get that the ln of e squared is 2. Let's try a couple of more powers of e. What about ln of e cubed? Let's call that a for answer. And another way of saying this is log base e of e cubed is something I'm looking for that I've decided to call a. That allows me to translate this logarithmic equation into, that's now an equation because I made it into one. That allows me to translate it into an exponential equation, and this would say e to the a, right? The exponent is the thing the log is equal to, the base is e. What's the answer I get when I use a as an exponent? This is saying I get e cubed. So a has to be 3, and since a was just my answer to what is ln of e cubed, that tells us ln of e cubed is 3. And I wonder if you can see a pattern here. Ln of e to the first power, let me put the invisible 1 in on part B here. Ln of e to the first power was 1, ln of e squared was 2, ln of e to the third power is 3. What do you think ln of e to the negative 1 is going to be? If you guess, just based on the pattern, that ln of e to the negative 1 is going to be negative 1, you are correct. Let's see how that goes. I'm going to call that a for answer. So this is saying log base e of e to the negative 1. I'm calling a. That's what I'm looking for. That's my unknown. So this in exponential form is saying e to the a equals e to the negative 1. That shows me that a must be negative 1. And yep, sure enough, since a was my name for the answer to ln of e to the negative 1, that shows that ln of e to the negative 1 is 1. So hopefully you're seeing that this ln and the e's cancel each other out. You don't need to write that down right now. We're going to write it down in just a little bit. I mean, about the canceling thing. Okay, ln of 0. That's actually a trick question. Do you see why? Let's give it a for answer. So this is saying log base e of 0 is a. Now, if I translate that into exponential form, this is saying e to the a equals 0. Now, this can't happen. If you take a positive number like e and raise it to any power, you are never going to get 0 as an answer. So, since this can't happen, that tells us that the ln of 0 just does not exist. It looks like a number, but it's not a number. It's a meaningless collection of symbols. And the reason I was hoping you might, if you're sharp-eyed, have spotted that this was a problematic question, remember that we said that for any base, you can't take the log of 0. We did that up towards the beginning. So that includes log base e. You can't take the log of 0. It just doesn't exist. What about the natural log of -1? What did we say about taking logs of negatives? Yeah, we said we can't do that. So ln of -1 also does not exist because, as we observed above, you just cannot, it doesn't matter what the base is, you cannot take the log of a negative number. So I'll write that out to be more general. Log of a negative just doesn't exist. So these two facts came out of looking at the graph of our log function where there's no negative x values on the graph, and x equals 0 does not exist on the graph either, right? Because the graph never touches the y-axis, so there's no point where x equals 0. And let me just, since we're talking about ln of -1 too, let's just put that in as well. The graph, there's no dot on the graph where the x-coordinate is -1, only positives. So we can say does not exist. And if you want, you can go through this exercise too, where we say, okay, log base e of -1, what is that? I'm going to call it a for answer. Then translating this into exponential form, this is saying e to the a equals -1. And that can't happen because if you take a positive number and raise it to a power, you're never going to get a negative answer. So this can't happen. This video is getting pretty long, so I'm going to stop there and we'll pick up from there in the next video.